So looking at chapter 17, we're looking at solubility. And just as a refresher, solubility is defined as the maximum amount of solute that can be dissolved in a solvent at equilibrium. And equilibrium is the state at which the concentrations of products and reactants are constant after the reaction has taken place. And that solubility product constant, the KSP, describes the equilibrium between a solid and its constituent ions in the solution. And that value of the constant identifies the degree to which the compound can dissociate in water. So our first example, silver cyanide, we would write this added to water. So I have my solid salt added to water, and my silver cyanide is going to break apart into Ag+. Now it's dissolved in aqueous solution, AQ, Cn minus. So to write that, KSP, again, products over reactants. So I would look at, say, KSP is equal to Ag+ times Cn minus. And again, we do not use solids or liquids in KSP expressions. So that is where we would finish. Nickel carbonate. So I have nickel carbonate, again, added to water. My nickel is Ni+2 over here in my products. And CO3 is going to also be -2. So my KSP expression would be the concentration of Ni+ ions times the concentration of CO3 -2 ions. And gold bromide, AuBr3, again, plus water, so I'm going to have Au plus 3 ions plus 3 bromide ions. Br is -1. Look at your periodic table to double check. So my KSP expression would be the concentration of Au plus 3 ions times Br minus ions, and that would be to the third power. Again, remember from our previous chapters, that coefficient becomes the exponent. Looking at number 2, we're going to use the KSP values to decide which compound in each of the following pairs is the more soluble. So you're going to look at the appendix in your text, and in this text it's Appendix J. Now the higher the KSP, that means the more salt will dissolve until equilibrium is reached. So therefore, higher KSP values is higher solubility. So the one that is more soluble. If I look in the appendix, PbCl2, you should see its solubility as 1.7 times 10 to the negative 5. And lead bromide is 6.6 times 10 to the negative 6. So this 1.7 times 10 to the negative 5 is the larger value, so higher solubility. Looking at mercury sulfide or iron sulfide, so mercury is 4 times 10 to the negative 54. That's the HGS. Iron is 6 times 10 to the negative 19. Obviously, the negative 19 is larger than negative 54. That is very small. So that would be FeS. And for the last one, looking at iron 2 hydroxide versus zinc hydroxide, the iron hydroxide is 4.9 times 10 to the negative 17, and zinc hydroxide is 3 times 10 to the negative 17. So the 4.9 times 10 to the negative 17 is larger than 3 times 10 to the negative 17. For number 3, we're going to calculate the KSP from the solubility. So we have a 1 liter sample of a saturated calcium oxalate solution, CaC2O4, calcium oxalate. We know how many grams of the salt we have. We want to calculate the KSP. So let's write our equilibrium expression. Here's our calcium oxalate, and we know it's going to, when added with water, this is our solid, and added with water, it's going to break into the Ca+2 aqueous ions, and C2O4 aqueous. We know that calcium is +2, so this must be -2 according to this compound expression. So it's a 1:1:1 ratio. Our KSP expression would then be our calcium ions times the C2O4 -2 ions. Now we know that we have 0.0061 grams of calcium oxalate. Whenever we have grams, we need to get to That's right, we need to get to moles. So I'm going to, I know this got cut off by my hole punch here, 0.0061 grams. And I found the molar mass of 1 calcium, 2 carbons, and 4 oxygens was 128 grams of calcium oxalate. So I went grams to moles, and I got 4.76 times 10 to the negative 5 moles. We were told it's in 1 liter, so we need the concentration. So moles divided by liters gives me the 4.76 times 10 to the negative 5, capital M. We know that we have a 1-to-1 ratio, so if that's the concentration of the calcium oxalate, we know that that's going to be equal to the concentration of calcium plus 2 and equal to the concentration of the oxalate. So if we know that concentration and that concentration, I can simply multiply those two together to get the KSP. So 4.67 times 10 to the negative 5th squared, or times itself, would give me 1.08 times 10 to the negative 13 for our KSP value. We're looking for number 4 at solubility in the common ion effect. What's the molar solubility of calcium oxalate in 0.15 molar calcium chloride? And we're given the KSP for calcium oxalate is 2.3 times 10 to the negative 9. So we found the KSP for calcium oxalate up here, but obviously it's going to be different if it is in calcium chloride. So we're going to use the same equation from number 3, but now we have additional Ca plus 2 ions because it's in calcium chloride, which is CaCl2, and we know that that's going to be Ca plus 2 ions and Cl minus ions. But this is what we're most interested in. So we want to say, therefore, the solubility, so the KSP for that calcium oxalate, this is our Ca plus 2, and the oxalate was the C2O4 minus 2, but now we have an additional concentration, the 0.15 molar calcium from the calcium chloride. So what we can do is we can say the KSP, 2.3 times 10 to the negative 9 that we're given, is equal to, we know that the calcium and the oxalate were 1-to-1 molar. So we can just say X. X plus 0.15 times X. All right. Now, KSP, that solubility constant, this 2.3 times 10 to the negative 9 is a very small number. It is a lot smaller than 0.15. So we can rewrite X plus 0.15 as just 0.15 because a teeny number plus 0.15 is going to be 0.15 with 7 zeros after it and then a 2, 3, right? That's what that is. So that is such a small number, we're just going to write it as 0.15. So I'm going to rewrite this and say that the KSP is equal to 0.15 times X. And then we can solve for X, and we get X is 1.53 times 10 to the negative 6 molar. And that would be our concentration for the oxalate ions as well as the calcium ions from the calcium oxalate. So the molar solubility of calcium oxalate would be 1.53 times 10 to the negative 6. Looking at number 5, we want to predict whether precipitation will occur. The concentration of calcium ion in blood plasma is 0.0025 molar. If the concentration of oxalate is 1 times 10 to the negative 7, do you expect calcium oxalate to precipitate? The KSP for calcium oxalate is 2.3 times 10 to the negative 9. Okay, so let's use the same equation as we did up here in number 3. Knowing our KSP is the concentration of calcium times the oxalate. So our ion product is 0.0025, that's our calcium, times the oxalate, 1 times 10 to the negative 7. And when we do that, we get 2.5 times 10 to the negative 10, which is smaller than its KSP, the 2.3 times 10 to the negative 9. So because that is smaller than the KSP, we would not expect calcium oxalate to precipitate. Let's look at number 6. We have 1 liter of water is able to dissolve 7.1 times 10 to the negative 7 moles of silver bromide. What's the KSP for the salt? All right, so let's write out silver bromide, solid. It's going to dissociate into Ag plus and Br minus ions, and we know this is a 1 to 1 to 1 ratio. So if I have 7.1 times 10 to the negative 7 moles of silver bromide, I also have that many moles of Ag plus and that many moles of Br minus, and it's all in 1 liter. So that's 7.1 times 10 to the negative 7 m. That's our concentration of our Ag plus and our Br minus ions because of those 1-to-1 ratios. So my KSP is going to be concentration of Ag plus times the concentration of Br minus, which are both the same, and we should get 5.04 times 10 to the negative 13. Number 7. What is the molar solubility of iron hydroxide, iron 3 hydroxide, in a solution having a sodium hydroxide ion concentration of 0.05 molar? And we're given the KSP for this iron 3 hydroxide. Well, so here's what I'm going to do. Our iron 3 hydroxide, we know is going to dissociate into the Fe plus 3 ions and 3 OH minus ions. So I'm going to make an ice table here. We know we don't include our solids in initial concentrations because solids don't have concentrations. And we know that initially I don't have any products, except I do know initially I was told it's in a sodium hydroxide ion concentration of 0.05. So we do have some product, that hydroxide. So we have 0.05 initially. And we know that our change, again, we don't take into consideration solids because nothing's going to happen, but we lose reactant, we gain product. And so we're going to gain X and we're going to gain 3X because of that 3 hydroxide there. And then at equilibrium, what am I going to have? 0 plus X is X. 0.05 plus 3x is 3x plus 0.05. So let's write that into our KSP expression here. So we know KSP is our Fe plus 3 concentration and our OH minus concentration to the 3rd power. So I'm going to plug in here our KSP value that we were told, the 1.6 times 10 to the negative 39, is equal to X from our ice table times 3x plus 0.05 cubed. Now remember that X value here, we can make that assumption that it's so small it's not going to impact that number at all. So we can just pretend like that doesn't exist and do 0.05 cubed times X to equal 1.6 times 10 to the negative 35. And that would solve for X. X is 1.28 times 10 to the negative 35. And X is equal to my Fe plus 3. That is a 1-to-1 ratio with my FeOH3, my iron hydroxide. So that would be the concentration of the iron hydroxide. Do the math. Double check, make sure you get the same thing. Number 8, we have lead iodide, PbI2. We're given its KSP value. What's the molar solubility of PbI2 in water? Okay, so let's write out our PbI2 expression here. So PbI2, again, solid, dissociated into our aqueous ions here. And if I was to give values here, we have a 1 to 1 to 2 ratio. So Pb is going to be X. That means that I is going to be 2X. So our KSP expression is going to be KSP is equal to X times 2X, and that is squared because of my 2. All right, so then when I distribute this, I'm going to get 4x squared times x, which is 4x cubed. So our KSP is equal to 4x cubed. And that KSP is 7.9 times 10 to the negative 9. It's 4x cubed. And let's solve for x. So I'm going to divide both sides by 4 and then take the cubed root, which means I'm going to multiply by 1 over 3. And that gives me 1.3 times 10 to the negative 3m. For number 9, it's kind of similar to number 7. The molar solubility of silver iodide in 0.2 molar of sodium iodide solution. So I'm going to take my silver iodide and break it down into my Ag plus and I minus. And remember, solids initially, I have, again, not concentrations for solids, and I initially have normally no products, except here I have a common ion. It says that I am in 0.2 molar of NaI. So notice that iodide is a common ion, and I have 0.2 iodides initially instead of 0. So remember, I gain product, and so I would have X for my silver and 0.2 plus X for my iodide, and that is going to be thrown into my KSP expression. KSP is my products, Ag times I minus. So I'm going to put my Ag, which is my X, and my 0.2 plus X. But again, my assumption rule, I'm going to assume that that X is very small. So I'm just going to take 0.2 times X and divide both sides by 0.2. And I would get 4.15 times 10 to the negative 16 would be equal to X, which is my Ag plus, and that's a 1-to-1 ratio with AgI. So I would assume that 4.15 times 10 to the negative 16, and actually I believe I only need 2 significant figures, so 4.2 times 10 to the negative 16. For the last problem, we're told that aluminum chloride reacts with phosphoric acid, aluminum chloride, phosphoric acid, to give aluminum phosphate. The substance is used in industrial and adhesive binders and cements, and we want a balanced equation. So we can see here that aluminum phosphate, so it's a double replacement reaction, that's our solid, and we have HCl, so we have 3 hydrochloric acids also produced. For part B, it says if we begin with 152 grams of aluminum chloride and 3 liters of 0.75 molar phosphoric acid, what is the theoretical yield of aluminum phosphate? Well, I'm going to start first with this 152 grams, because we know if I have 152 grams, I can get to moles of that aluminum chloride. And so I did right here, found the molar mass. I know how many moles of aluminum chloride I have, so I'm going to then look and go, well, if it's a 1-to-1 ratio, if I know if I have 1.1 for moles of aluminum chloride, I'm going to have 1.14 moles of product made. So it's a 1-to-1 ratio. There we go. Now let's look at our phosphoric acid. We're given volume and concentration of phosphoric acid, so I can find how many moles of phosphoric acid I have, right? Because moles is concentration times volume. So I have 2.25 moles of H3PO4. Again, it's a 1-to-1 ratio. So can I create 1.14 moles of product or 2.25 moles of product? This is my limiting reactant, right? This would be my excess reactant. Now, so that would be, I don't know, I didn't need to go one step further. I could say I would end up with 1.14 moles of AlPO4. If we placed 25 grams of aluminum phosphate in 1 liter of water, what are the concentrations of the aluminum and the phosphate ions at equilibrium? And we're given the KSP for aluminum phosphate. Now, we know KSP is the aluminum ions times the phosphate ions. It's a 1-to-1 ratio. And we're given the KSP for aluminum phosphate. So looking at this two different ways. My first thought is, okay, I'm going to go from grams to moles. 25 grams, and I found the molar mass of aluminum phosphate, 126 grams. So that would be moles divided by 1 liter. That would give me the concentration, 0.205 m. But that exceeds the solubility of the salt. It tells us the KSP is 1.3 times 10 to the negative 20. So we need to look at this expression and solve for x. X times x is equal to that KSP, the 1.3 times 10 to the negative 20. So take the square root of both sides. X must be 1.14 times 10 to the negative 10 m. And looking at part D, does the solubility of aluminum phosphate increase or decrease when we add HCl? So if we add HCl, HCl is going to add H plus ions, which is going to decrease the pH. It's going to make it more acidic. And by doing that, it will increase the solubility, right? Because that HCl will react with all of those phosphate ions. But it's not going to affect it by much.